Hi. So in this lecture, we will learn about, a lot of things. They're all connected together. So one would be random variables, probability mass functions, or PMFs as they are called, um, PDFs or probability density functions, and CDFs, which are cumulative distribution functions. So these are a lot of topics, in chunks, but they're all connected together, and we sort of need to learn them together to have an understanding of how they're connected with one another. So just a recap of the basic things that we need. We're dealing with probability here, so we need a sample space. When you have an experiment, you have a set of outcomes. So, for example, if you're rolling a die, you would get the outcomes as 1, 2, 3, 4, 5, 6, and those would be the set of outcomes for the experiment. And if you put them all together, you can call that S, or the sample space. Okay, if you're tossing a coin, heads and tails could be the two outcomes. Well, they are the two outcomes, and as a set, that would be the sample space, or so to speak. It's the universal set on which we are going to do or work out probability problems. This is the power set of the sample space. In other words, the set of all sets, or set of all subsets of S. So those are all the events as they're defined. Events are defined as an event is a subset of the sample space. This is the power set, which means that it not only contains all the subsets, all the non-trivial subsets. It also contains the trivial subsets, which are phi, that is the null set, and the set S itself. Okay, they are both in the power set. So this is the null event, and this is S, the certain event. Okay. So we know what probability is. It's just a function from the set of all events to 0 and 1, satisfying. The probability of a null set would be 0. That just makes sense. And the probability of the certain event is 1. It's a certain. Okay. So that's why it's called a certain event. So with probability 1. And if you have a set of events, for example, A1, A2, A3, like that for an experiment, and if they're all disjoint, in other words, as subsets, because they are events, they are subsets of S. In other words, they're in the power set. And if they're all disjoint as sets, then this is the rule that probability follows, the probability function follows. So if you take the probability of the union, which also this will also be a subset of S, so an event. Okay, so that's why this thing makes sense. So probability of this huge event here, this union could go on and on forever if A1, A2, A3 is an infinite set. It could also end if it ends at a certain AN, for example. Okay, it doesn't matter. So basically, what you need is a countable set or a list of events which are disjoint from one another, mutually disjoint. AI and AJ are disjoint. That their intersection is null. If you have such a list of events, then the probability of the whole thing together as a union can be broken up into the sum of the individual probabilities. Okay, so that's a handy identity that we can have. Then we have this new concept of a random variable, which really is a function, but written as an x. Okay, as a variable, just as we write variables. But it really is a function from the sample space to real numbers. Okay, so for example, if you have a box where, for example, this is a box, and let's say you have 3 red balls in there, 4 white balls, okay, and two black balls in there. Okay, so instead of calling them red, white, and black, for example, I can give them numbers. Okay, so if it's a red ball, I can call it 1. If it's a white ball, I can call it 2. If it's a black ball, then I can call it 3. Okay, so in other words, this is the sample space for the experiment that I'm doing. It's a box which contains all these balls here, colored balls. and I'm just defining a random variable. In other words, I'm just defining a function from this whole S. This is the set S, the universal set of all the outcomes. And instead of calling them by their names or their characteristic, I'm just giving numbers, assigning numbers to them. Okay, so that's what it means. So when I say 1, I just mean the set of all red balls here. Okay, when I say the number 2, I mean the set of all white balls there. If I say the number 1 and 2, I would mean the set of red balls and the white balls together. Okay, so it's just a way of coding the outcomes in terms of numbers. Okay. Well, you could define it in some other way also. You can call this 1, 2, 3. You can number them differently. But that's just one of the ways it's a random variable. It's one of the random variables that you can define on this set S. And if you have, and so the image set, okay, of this function, in other words, the set of numbers which are assigned to the outcomes, that is called the spectrum of X. Okay, so for example, in this case, only 1, 2, 3. So spectrum of X in this case will be only the numbers 1, 2, and 3 because these are the only assignments done to the outcomes. Okay, if you have another ball, for example, a pink ball, and you call it 4, then you would have number 4 coming in here. Okay, whatever. So the assignments. We leave out the rest of the numbers, okay? The rest of the real numbers are not listed in here. So that's the spectrum, the image set. Now we call this random variable X discrete if this set, the image set, is countable. Okay, by countable I mean again it can be finite, it can be infinite. Things inside that set will have to be you'll be able to list them. In other words, you'll be able to enumerate them. Okay, so they're countable. You can count them 1, 2, 3, 4 like that. Okay, so for example, if the spectrum here contains these elements, I can call this one x1, I can call this one x2, I can separate one from the other, and I can do that. Okay, it can be a finite set, it can be an infinite set. For example, 1, 2, 3, 4, 5 is a finite set. It's a countable set because I'm counting 1, 2, 3, 4, 5. If I go on and on, 1, 2, 3, 4, 5, 6, 7, 8, on and on, it's an infinite set, but still countable because I'm counting 1, 2, 3, 4, and I'm separating one number from the other. Instead, if I give you this set, 0, 1, the set of all numbers, all real numbers between 0 and 1, including 0 and 1, this is the closed set, closed interval. In that case, this is not a countable set because you know the first number, it's 0, then you don't know which is the next number. Okay, so you can't really separate numbers. So that's not a countable set. So if you have a countable set, if the spectrum is a countable set, then X would be called a discrete random variable. Okay, for example, in this one, because it's a finite and a countable set, any finite set will be countable. Because this is countable, 1, 2, 3, that's it. This random variable which I've just defined, X, from this set S to real numbers, this is a discrete random variable. Well, now we come to a little more sophisticated definitions, and these are the topics today. So one of them is, so I can look at, so in this example, if I ask you what's the probability of picking a red ball from this box, okay, which is really the rectangle represents the box, and these are the balls in there. So if I ask you what's the probability of a red ball, well, how many balls are there? So there are 9 of them, okay, 3 and 4, 7 and 2, 9, and it's going to be 3 out of 9, okay, because there are 3 red balls and 9 possible choices. So the probability that you would pick a red ball from this box would be 3 by 9, and that's written as probability X equals X1. Okay, X1 here is number 1. Okay, so in other words, in this example, if I ask you if I ask you a probability x equals 1, okay, that's just asking what are the x equals 1 represents a red ball. So what's the possibility or what's the probability of picking a red ball? This is the mathematical way of asking the question, which I'm asking in language. Okay, so if you consider these things xi's, in other words 1, 2, 3, for example, in this instance, if I write down x equals xi, that's a number, that's a probabilistic number, so it has to be between 0 and 1. I'm going to call it fxi, which is obviously f I'm defining as a function from the spectrum. Okay, so the spectrum here in this example is 1, 2, 3. If I define a function in this spectrum as f, so in this example, f would be from 1, 2, 3 to r, and so these are i's, so fx1, in other words, the first one, the first one is 1. F of 1 is the probability that x equals 1, and we just calculated that it would be x equals 1 means the red ball, so 3 out of 9 possibilities. Okay, if you ask me for f equals 2, the next one, okay, the next in line, the next element in the spectrum, that would be probability that x is equal to 2. Now x equals 2 represents the white balls. Okay, so that would be 4 over 9. Okay, and f of 3, which is the third possibility, okay, that is probability x equals 3. Well, x equals 3 represents the black balls, which are 2 of them, so you have 2 by 9. Okay, so this function f, which I've just defined by making use of the probability function, this function small f is called the probability mass function, and it's defined on the spectrum. Okay, only on the spectrum. So in other words, 1, 2, and 3. Well, if you want, if some authors want, they can extend this function to all real numbers. In other words, for example, 1.5 is in there. According to this definition, the function is not defined on 1.5 because 1.5 is not a spectral point. Okay, the spectral points are only 1, 2, and 3. But if you want, you can define it on 1.5 and say that the f of 1.5 is 0. Okay, so in other words, you can extend this function to all real numbers in the fashion that whichever point is not a spectral point, you can define f on that point as 0. That's a way to extend that function. So I've written it out here. What does this mean? And I've already explained it. X equals xi. In other words, x equals x1, for example, meant whichever points in the sample space. So this was a sample space. Whichever points, these 3 points in a sample space, whose function value or x value was xi. In other words, whose x value, when x acts on this, takes it to the point 1. Okay, so that's which is really the inverse of the point 1 in this example, or xi. Okay, right, and so that's the probability mass function, which is really abbreviated as PMF, and you would hear me say PMF a lot. And finally, we define what is called the cumulative distribution function, which is the CDF for short, which is really a function capital F. It's denoted by the letter capital F. And let me just write that down once more because it's written right at the bottom. So I'm going to rub this out because it's taking up a lot of space and you know what we're doing. So I'm going to define the CDF. Okay, the CDF really is a function capital F, which is defined on all real numbers. Okay, from all real numbers to, well, real numbers, but they will turn out to be between 0 and 1. Okay, it's defined like this. So if you take any number x, small x, from R, then f, capital F of that small x is defined as the probability that the random variable takes values less than equal to this value small x. Okay, So in our example, let's just draw that back. This was the box with 3 red balls, 4 white balls, and 2 black balls. The red balls were all numbered 1, the white balls were all numbered 2, and the black balls 3. That's your random variable. This is the sample space, and this is the set of all real numbers, out of which I'm picking only 1, 2, and 3. So really, they're all real numbers. And this set of 1, 2, 3, this is really the spectrum of X, or the image set. Okay, so if I ask what's f of 2.7, for example, because I can take any point, any decimal points also, because f really is defined on all real numbers, and 2.7 is a very general, it's a real number. So this would be the probability that x is less than or equal to 2.7. Well, what are the numbers? What values of capital X? So by values of capital X, I mean the spectral points, the values that it can take as a variable. X can take the value 1, X can take the value 2, X can take the value 3. So what values of X are less than or equal to 2.7? They are 1 and 2, not 3, because 3 would be more than 2.7. And so this really is, this really means X less than or equal to 2, because they're the same. There will be no value, more than 2 here, okay? So it has to be less than or equal to 2. These two make the same meaning as an event. So, and what are those? So the probability, so X less than or equal to 2 means which event? So all red balls and all white balls. Because red balls take the number 1, which is less than or equal to 2. White balls take the number 2, which is less than or equal to 2. So this really is a set of all red balls and all white balls, and that probability is, how many are there? So there are 4 and 3, 7 out of 9 possibilities. So really, the f of 2.7 is 7 by 9. Okay, so we've just defined, by a practical example, what it means to say f of some number. Okay, capital F of some number. Well, this actually gives another insight, is that probability X less than or equal to 2 really means there are 2 events here. Either X can be equal to 1 or X can be equal to 2. Okay, because X less than or equal to 1 means X can take the value 1 or X can take the value 2. When X takes the value 1, it means all the red balls. And when X takes the value 2, it means all the white balls. And so X equals 1, this is X equals 1. And this one is X equals 2. And X1 is this event, because it's a subset of the whole set. X equals 2 is this event. This is a subset of the whole set. And they're disjoint. You see, the red balls and the white balls are separated. So just by the axiom of probability, which we have written out in the previous board, this can be broken up. Because these 2 events are disjoint, this can be written out as probability X equals 1 plus probability X equals 2. And obviously, the first one is 3 out of 9, and the second one is X equals 2 means how many white balls, so 4 out of 9, and that just gives 7 out of 9. So you could have, instead of doing it like before, you could have broken it up into individual events and then calculated it. That's the same thing. So in other words, what we see is, if you have, x1, x2 up to xk, for example, are spectral points. In other words, what I mean by spectral points is they belong to the spectrum of X. Okay, spectral points such that they're all these x1, x2s up to xk, they're all less than or equal to some number x, small x. Small x. Okay. then if somebody asks what is capital F of the small x, it will be, well, by definition, it's the probability that the random variable x, capital X, takes less than equal to small x. But all these are the spectral points less than equal to small x. So they will be, as before, you would have the sum of all px equals x1 plus px equals x2. This goes on up to k, x equals xk. Okay, so that's a small proof that we have done here. Okay, in other words, this can be written as, if I give you this, it can be written as a formula, for example. All the pxi's, okay, such that xi, well, it's a spectral point, and xi is less than equal to this small x. Okay, you can think of this. This is just a special case. I mean, this is how was the application of this formula. Okay, so that's what I mean by a probability, a cumulative CDF, cumulative distribution function, CDF. Okay, it just means it's related to probability, and these are, if you remember, these are all FXIs. These are all the probability mass functions, PMFs. Okay, so these are all, so they were written as FXI, okay, from the previous board. That's the PMF, which is defined as probability x equals xi. And so this is the same thing again. Xi is a spectral point, and xi is less than equal to x. So this is how the CDF is related to the PMF, okay, the probability mass function. CDF at a point is equal to summation of some PMFs, okay, which follow this condition. Right. So now if I ask for example, if I want to draw the graph of this function, which is defined on all r, so I should be able to draw this graph, okay. So let's say I have this graph. This is all of r. The horizontal axis is real numbers. Obviously, this is also real numbers, but I'm going to plot capital F on this, and I'm going to plot this R, the domain, on the horizontal axis. Okay, so let's just do that. Okay, what if I take an x? Okay, suppose x is a point. Suppose some x, small x is here. X is a point which is less than equal to. Let's stick to this example. If it's less than 1, for example, what happens then? Then what is capital F of this small x, which is less than 1? Okay, well, it means that it should be equal to the probability of this event where capital X, the random variable, takes values less than equal to 1, or x, which really is less than 1. Okay, so in other words, you have to have this event probably where capital X takes values less than 1, but it does not take any value less than 1. This is the smallest value it takes. It takes only 3 values, 1, 2, and 3. So this really is a null event. This condition does not match up with the how we have defined capital X. You can't have a value of capital X which is less than 1. So this really is a null set, and we know what null set produces for probability. It's 0. So any number which is less than 1, if I have 1 in here, any number x, for example, which is less than 1, it gives me capital F of that point is 0. So in other words, all these points which are less than 1, they all hit the 0 on the y-axis. Okay, so really, they're just. So let me just use another color. So all these points, before they reach 1, strictly less than 1, they're all, the function capital F is basically along the x-axis, y is equal to 0. Okay, what happens when x is more than 1 but less than 2. Well, in that case, capital F of this x is probability, this is capital X less than equal to small x, obviously. This is by definition, this small x. But this small x is less than 2. So I'm basically looking for an event where capital X takes a value less than 2, strictly less than 2, but that is only 1. Okay, which is capital X equals 1. This really is capital X equals 1. Because small x here is more than equal to 1. And it's less than 2. So capital X, what value does capital X take? Less than 2. It's only 1. Okay, and we know what that is. That is probability X equals 1 is 3 out of 9. So anywhere between 1 and 2, including 1, but less than 2, this function takes a value 3 by 9. So somewhere up here, so suppose this is 3 by 9 on the y-axis. So starting from 1, this includes 1. So I have this solid circle here. The open circle is for not including the point 1. Up to 2, and I have an open circle because it does not include 2. It's before, when x is before 2. Okay. Well, what would happen if I have a number x which is greater than or equal to 2, but less than 3, which is the last 3 is the last spectral point, or the greatest spectral point. In that case, capital F of small x is probability x less than or equal to small x, but small x is less than 3. So what are the points which are less than 3? 1 and 2. Okay, so that is probability x equals 1 plus probability x equals 2, and we know what they are. This is 3 by 7 and 4 by 7. So really, it's 7 by 9. The same case as this. Okay. You see, less than 3, strictly less than 3 and less than or equal to 2, they're again the same thing. Okay. Because they always produce x equals 1 and x equals 2. Right. So in this case, I have, suppose, so this value between 2 and 3, if I have 3 in here, so, and I have 7 by 9 somewhere on the y-axis, 7 by 9 somewhere here on the y-axis. So between 2 and 3, including 2 but less than 3, so including 2 but less than 3, I have this function, capital F, in this range between 2 to 3. It's there, okay? And so finally, I need to check what would happen if x is greater than or equal to the last spectral point, the greatest spectral point. In that case, f of small x is probability capital X less than or equal to x, okay, which is 3. So that's by definition, okay. And if it's a number which is more than 3, for example, then, for example, if this is 3.1, then what are the values that capital X can take? It can take 1, 2, and 3. If it's 3, if small x is 3, then also it can take 1, capital X can take 1, 2, and 3. So this really contains all the possible spectral points. So it's going to be probability x equals 1 plus probability x equals 2 plus probability x equals 3. And, well, even if you don't break this up, so because it contains all the spectral points 1, 2, and 3, it means as an event, it includes all the balls here. 1 includes all the red balls, 2 includes all the white balls, 3 includes all the black balls. So all of them, so this event, x less than or equal to small x, really means the whole set capital S. So this really is the whole set capital S, which is 1, okay. So if we have 1 somewhere here, starting from 3, going on and on up to infinity, you're just going to have 1. So starting from 3, including 3, you're just going to have 1. So here is the function, the graph of the function, capital F, the CDF. So it lies along the horizontal axis till it reaches the first or the smallest spectral point. Then it takes a jump, which is equal to the PMF. The PMF, that is f of 1, is probability x equals 1, and that is 3 by 9. You see? And this is the jump at 3 by 9. And then it continues between the first 2 spectral points and up to the second spectral point. Then there's a jump. How much is this jump? This jump is the same as probability, the probability mass function at 2. The probability mass function at 2 is probability x equals 2. And x equals 2 means the white balls, so that is 4 by 9. You see the jump from 3 by 9 to 7 by 9, this is 4 by 9. And then it continues like that till the last point. And then again there's a jump. And that jump, now you can guess it. That jump is the PMF at 3. Because the PMF at 3 is the probability x equals 3. And x equals 3 means the black balls, so which are 2 out of 9. So from 7 by 9 to 1, this jump is 2 by 9. Okay, and then it remains like that. So these jumps are really small f at 3, the PMF at 3. This jump is the small f at 2. This jump is the small f at 1, the PMF at 1. Okay, so that's how. This is the graph. It's a step function. It's an increasing step function. That's the graph of CDF. And really, if you look at it, this function, capital F, is discontinuous at all the spectral points because there's a jump. Okay, the moment there's a jump, there has to be a discontinuity. But it's discontinuous from the left because you're approaching from the left. And then, for example, at 1, before 1, this was a continuous function because there are no breaks in the line. But at 1, as you approach 1 from the left, at 1, there is a jump. So there is a discontinuity from the left. And then again, before 2, there is no discontinuity. But at 2, there is a discontinuity, but again from the left. Okay. And if you look at it, this function it's left discontinuous, but it is right continuous. Okay. So it's right continuous because it doesn't matter how you approach. Suppose so all these points are continuous. Wherever there are no breaks, obviously it's continuous means it's right continuous and left continuous. But let's look at this point. The point 3, of course, we've established that here the function is left continuous because as you approach 3 from the left, there has to be a jump. But as you approach 3 from the right, even at 3, so for example, if you're at 3.1, the value at 3.1 is the same as the value at 3, the value of f, okay, the same length. So if you take 3.05, so you approach 3 more, even then the value at 3.05 is the same as value at 3. So it doesn't matter how much you come close to 3 from the right, it remains equal to the value of 3. So there is no discontinuity from the right. Okay. And that's the same case with all the other points. So this function, capital F, really, so let me just write that down. So if I have to this is the last bit of this lecture here. If I have to sort of summarize the properties of CDF, I would say the first point would be that if you have, well, if this is the spectrum, if the spectrum is, for example, x1, x2, like that, okay. Well, I actually don't have to define it in terms of the spectrum. You can just see that the first point. So capital F at minus infinity, for example, as you take this x to minus infinity, this will be 0 because before the first spectral point, the function value, the capital F, is 0. even if you don't have the first spectral point, perhaps the spectral set is this spectral set is obviously finite, 1, 2, and 3. If you have the spectral set, which is a set of all integers, for example, okay? So in other words, you have all the integers, which is a countable set, but still an infinite set, okay? So in that case, you don't know which is this first spectral point, but you know that if there was a spectral point in the beginning, before that it would be 0. So by that logic, capital F at minus infinity, it is 0. Okay. And similarly, you can say that the capital F at plus infinity, this is 1, because after the last spectral point, this is going to be 1. Okay. In other words, by the time you approach the last spectral point, you include the whole certain event. Okay, S, and so the probability gets to 1. And as you move away on the left, you move towards the null event. Okay, you are excluding more points, so you are moving towards the null event. So that way, the F at minus infinity is 0, and F at plus infinity is 1. Right. You may F is right continuous. At all points, okay, but is left discontinuous, sorry. The left discontinuous at all points in the spectrum of X, okay. And I've just told you what's the value of the jump, or the measure of the discontinuity, so to speak. Let's just write that down. If you take let X be a spectral point, then the value of F, capital F, at X plus, in other words, that's the limit. That really is. This is the limit F of, or let's just make it A, just for just for a constant spectral point. If you have X approaching A plus, in other words, if you approach the spectral point from the right, okay, that's the meaning of this. If A plus minus, if you approach F from the left. So, for example, if F is 3, A is 3, if you approach A 3 from the right, that's this number, it's going to be 1. The value is 1. And if you approach A from the left, which really is limit fx, x approaches A from the left, then this will be equal to the value of the PMF, probability mass function at A, which really is, that's the definition, x is equal to A. So, yeah, I mean, this is just this, and this is just this, okay? So that's more or less, with all the properties of CDF jotted down here. I think we will finish it here. So more or less, you can see how things are connected. We haven't touched on one thing. We missed out on what would be the probability density function, PDF, which we will cover in the next lecture. And that's the case when x is not a discrete random variable, but x is a continuous random variable. So in this lecture, we covered only, we've talked about only x, the random variable being, a discrete random variable, because the spectral points are all countable. Okay, so the spectrum is countable. The spectral points are all distinct. Okay, so I think we will finish this here. Take things forward in the next lecture. Okay, thank you.